Water and bugs ate this building alive. Here's the strange part. Every piece of wood you've ever touched is dead. It's basically a wall of drinking straws, packed together by the millions, and every single straw still remembers exactly which direction it was pointing when the tree was alive. That memory is why wood behaves nothing like steel or concrete, and why it can quietly destroy an entire building if you ignore it. Cut a tree trunk open, and you'll see rings, one per year of growth, plus an outer ring of sapwood that was still carrying water and nutrients, and an inner heartwood core that's basically retired, just there for structural support. Because of that straw-like structure, wood is what engineers call anisotropic and inhomogeneous, two fancy words that just mean its strength completely depends on which direction you're pushing, pulling, or cutting it. Try to imagine a steel beam that's strong lengthwise, but crumbles if you push sideways. That's wood. Here's the master property that controls almost everything else about wood: density. Sounds simple, mass divided by volume, but wood is basically a sponge. The solid cell wall material alone is incredibly dense, around 1,500 kilograms per cubic meter, but 60 to 80% of any piece of wood is actually empty space, hollow cell cavities. So the density you measure is really just how much of this sponge is solid wall and how much is air. And sponges, as you'd guess, love water. Wood is hygroscopic. It's constantly trying to match the humidity of whatever room or forest or basement it's sitting in. Leave a wooden beam in a damp cellar, and it will pull moisture out of the air and hold onto it, whether anyone wants it to or not. But here's the part that gets weird. Below about 30% moisture content, a threshold engineers call the fiber saturation point, something changes. Above that point, water is just sitting loose inside the hollow cavities, and the wood's actual size doesn't change at all. Below it, the water is soaking directly into the cell walls themselves, and that's when the wood physically starts to shrink or swell. And it doesn't shrink evenly. For every bit it shrinks along its length, it shrinks about 12 times more across the rings, and roughly 24 times more around them. That's why a wooden door swells shut every summer and leaves a gap every winter. It's not warping randomly, it's following a precise, predictable ratio, in three completely different amounts, in three completely different directions. This isn't just an annoying door problem, it can quietly wreck a building. Picture a timber beam installed while still slightly damp, say 20% moisture, that later dries down to a stable 12% indoors. Run the math, and that single beam can shrink by roughly 5 millimeters. Multiply that across a whole floor of beams stacked on top of each other, and suddenly you've got measurable structural settling in a building nobody touched. And that same moisture is exactly what was quietly killing the building from our opening shot. Push wood's moisture content above roughly 20% for long enough, and you've built a 5-star hotel for fungus. Add trapped water, poor detailing, and a few decades of neglect, and rot doesn't just weaken timber, it hollows it out from the inside until a wall that looks solid can be crushed by hand. So how do engineers fight an organic material that shrinks, swells, and invites fungus? Mostly, keep it dry and design it to stay that way. Buildings are sorted into exposure categories, from never gets wet all the way to permanently sitting in seawater, and every design decision follows from that. Roof overhangs are built to a strict 60-degree rule, so rain physically cannot reach vulnerable beam ends. And if a piece can't be kept dry, engineers reach for naturally rot-resistant species. Some tropical hardwoods can sit outside for decades untreated, while others, like common birch or beech, will rot in a few short years if left exposed. On top of all that, raw wood is wildly inconsistent. Two boards cut from the very same tree can have wildly different strength, just because one has a knot or a sloped grain or grew through a drought year. So before any piece of wood is allowed to hold up a roof, it gets graded almost like eggs at a farm. Inspectors or scanning machines check knots, grain angle, and even bounce sound waves through the board to measure stiffness. Only then does it earn a strength rating and a license to be trusted with a real structural load. which leads to the cleverest trick in modern timber construction. If a single tree trunk is unreliable, stop building with single tree trunks. Take short, graded, defect-free boards, cut their ends into interlocking zigzag finger joints, glue them end to end into long beams, then stack and glue multiple layers on top of each other. The result, engineered glue-laminated timber, is stronger and more predictable than the solid log it came from, and can be shaped into curves a real tree never could. Now push that idea one step further. Instead of stacking layers in the same direction, rotate each layer 90 degrees to the one below it like plywood, but scaled up to entire wall and floor panels. That single move cancels out wood's biggest weakness, its direction-dependent strength, turning it into a flat, dimensionally stable slab you can build multi-story apartment buildings out of. It's already happening. A former industrial brewery building in Berlin was recently converted using exactly this kind of engineered timber framing and paneling, standing many stories tall, built almost entirely from glued boards. So the next time you see a wooden beam, remember you're not looking at a simple stick. You're looking at a bundle of dead straws, fighting a constant battle with water, fungus, and its own inconsistency, one that engineers have spent over a century learning to outthink. But grading and gluing a beam correctly is only half the job. The real question is, once you trust that beam, how much weight can you actually put on it before it breaks? That's a very different and far more mathematical story.